It's a pleasure to have Dominik Schmid today in the seminar, who will talk about the mixing times for the TASEP on the circle. Dominik.
Thank you very much. Thanks a lot for the invitation, the opportunity to give the talk. So I'm going to speak about some joint work that recently with Allan Sly. And let me start right away by defining the main model of this talk, which is going to be the simple exclusion process on the circle. So for this model, we consider a circle of length n, so here in this case of length 7, and we place particles on distinct sides. So each side of the circle is occupied by at most one particle. So in general, we have like k particles on the circle of length n, and each of the particles receives some rate 1 Poisson clocks independently. And whenever the clock of a particle rings, it performs a jump to the right with probability p for some fixed p between 0 and 1, and to the left with probability 1 minus p. So let's say we're in this example here, the clock of this particle rings, then it tries to make a jump to the right at probability p. So in this case here, it jumps to an empty side, so this move is performed. However, let's say we would be in the case that this particle here would try to attempt a jump to like to the right or like in clockwise order. Then because there's already a particle sitting, this move is going to be suppressed. And this last constraint that we're not allowing two particles occupying the same site is also called the exclusion constraint, therefore the name simple exclusion process. Now, the question we're tackling during this talk is what can we say about the long-term behavior of this simple exclusion process when the length n of the circle goes to infinity. And the way we are going to like quantify this term, like what is the long-term behavior, this will be done using the notion of mixing times. So to introduce mixing times, let me first fix a bit of notation. So for the simple exclusion process on the circle, I think of it as a configuration at a time t, denoted by eta t in some state space omega and k, where like omega and k consists configurations with like for the circle of length n with k particles at time t. So I see there's some discussion in the audience. If there are any questions, just interrupt me at any point if there's anything unclear. Okay. Yeah, so let's think of the simple exclusion process here denoted as the process eta t as a continuous time Markov chain. And it's not hard to see that for any k between 1 and n minus 1 and any parameter p between 0 and 1, this is a irreducible Markov chain in continuous time. So we have a unique stationary distribution. And in fact, it's a nice exercise to see that this is the uniform distribution over all configurations on the circle of length n with k particles. So in the following, we try to specify the speed of convergence towards the stationary distribution mu. And we do so by using the total variation distance. So total variation distance is nothing else but a half times the L1 norm between the law of the process at time t and the stationary distribution mu. And we're looking here at some fixed starting configuration eta and compare the law at time t to the stationary distribution. So what we're going to do then is we're looking at the worst case distance at time t. So we're taking the maximum over all initial configurations in our state space and compare then the maximum, so the worst case initial condition for the process at time t with respect to the stationary distribution. And now the mixing time, or more precisely the epsilon mixing time for some epsilon between 0 and 1, will be the minimal amount of time t it takes, such that this worst case distance d and k drops below epsilon for the first time. And now in general, we want to study what can we say about this t mix of n and k when n goes to infinity. So let me start maybe as a little warm-up exercise for those of you who are maybe not too familiar with mixing time notation. And this is the simple random walk on the circle. So in this case, just think of k being equal to 1, and we're looking at the circle of length n. And I claim now that for any parameter p and any epsilon between 0 and 1, we know that the mixing time will be of order n squared. And to see this, well, the stationary distribution is clearly a uniform distribution on the state space. And what is like the time it takes to like converge to the stationary distribution? Well, the central limit theorem tells us that it's essentially taking time n squared, such that the deviations of the random walker are of order n. So this is maybe just like a very quick way of seeing this, and can also be made rigorous in this way. Okay, so keep in mind, so for a single particle, we see like a mixing time of order n squared. Now, there's a very nice result for like a general number of particles k due to Hubert-Lacroix, I think I also see in the audience. So, and this is in the case where p is equal to 1/2. So in this case, suppose that the number of particles k satisfies the case between 1 and n over 2, and that the number of particles k goes to infinity with n. Then in this case, when we look at the ratio between the epsilon mixing time and n squared log k, then for any epsilon between 0 and 1, this converges to 1 over 4 pi squared. And such a behavior that we see that the leading order of the mixing time does not depend on epsilon, actually, this is also known as the cutoff phenomenon. So let me maybe comment a bit on this result. So, so maybe first on the assumptions. So here we are in the case p is equal to 1/2. So the particles perform symmetric simple random walks on the circle. Now, this first condition here, that case between 1 and n over 2, I claim that this is not really a restriction. And to see this, note that when we have like this picture of the particle system on the circle, I claim that the mixing time is the same if we replace k by n minus k, simply because we can like exchange like the roles of particles in empty sites. So this first assumption is not really a restriction, and I will assume throughout the talk that k is always between 1 and n over 2. However, the second assumption here is a restriction, that the number of particles k goes to infinity with n. As we saw before, in the case where k is equal to 1, the mixing time is like still of order n squared, but such a sharp transition, such this cutoff phenomenon that the leading order does not depend on epsilon, this does actually not hold when k is constant. So this assumption here is really necessary. And let me comment also a bit maybe on what I mean here by cutoff, and this is can be nicely visualized as follows. So think of n being very large. Then if we look at the order of the mixing time, so this T mix of nk, and let me fix some epsilon, say epsilon is equal to 1/4, then we say that this family of Markov chains exhibits cutoff if we see the following. So at the beginning, the mixing, or this the worst case distance from stationarity will be very close to 1, and then within a small order, so small compared to the order of the mixing time, this total variation distance will drop from close to 1 to close to 0. And it's in general a very interesting question, which families of Markov chains do exhibit such a cutoff behavior and which do not. Okay, so let's now come to the case when p is not equal to 1/2, so when the particles do not perform symmetric simple random walks. And I'd like to treat one particular case, which is the totally asymmetric case. So in this case, p is equal to 1. So that means that the particles will only be able to move in the clockwise order. So whenever the clock of a particle rings, it will attempt a jump in like the clockwise direction. And again, it will do so under the exclusion constraint. So let's say this particle here will, for example, not be able to jump like on top of that particle. Okay. And for this dynamics, we have the following results. So again, based on joint work with Allan Sly, namely for any k between 1 and n over 2, and any epsilon between 0 and 1, there exists some constant C1 and C2 depending on epsilon, such that in the leading order, the mixing time will be, so the mixing time will be of order n squared k to the minus a half. And moreover, we can show that the cutoff phenomenon does not occur in this case. So what I mean by this is, okay, so we can really show that such a sharp transition does not, as before, does not occur. So these constants C1 and C2, they do need to depend on epsilon, actually. Okay, and maybe if you see this, this might be a bit surprising if you have the other result in mind. So before we had for p equal to a half, that the mixing time was of order n squared log k. So in particular, the more particles we have, the longer it takes until the system mixes. But here we see that the more particles we have, so when k goes to infinity, with n in particular, so in this case, the more particles we have, the faster the TASEP on the circle actually mixes. So this is something, yeah, which is maybe a bit strange, and which I will comment on in a second, or like explain more in more detail very soon. So yeah, so this behavior here is like very different from the case p equal to a half. And let me also mention at that point that in general, we believe that for all p not equal to a half, this is actually the behavior of the mixing time which should occur. Okay. So before coming to the proof, let me maybe comment on some related models. So there's one natural, or like say the simplest version maybe to study first, or to express like the exclusion process, which is on the segment. So consider a segment of length n, so from 1 up to n, and assume that the particles again jump at rate according to rate 1 plus of clocks, and jump to the right with probability p and to the left with probability 1 minus p. Then in this case, mixing times were also previously studied. So there's a result again that in the case where p is equal to a half, when k goes to infinity, again assuming that k is between 1 and n over 2, then the mixing time is again like of order n squared log k, this time with like 1 over pi squared. It's the constant in front, and we see that cutoff occurs. And also in the biased case, this is a result due to Serre-Labbe and Über-Lacroix that for any parameter p different from a half, we have that the mixing time is in fact of linear order, and this constant, and we have cutoff, whereas this constant c depends only on the ratio between k and n. So whenever this ratio converges to some constant alpha, this constant c, which like determines the leading order of the mixing time, will only depend on that that ratio or to whatever this ratio converges. Okay, and you see here again, there's like a so here again, like in the biased case, the order of the mixing time, so the mixing time is like much smaller compared to like the symmetric case. Okay, so
so a question. Yeah. So what are the boundary conditions that you are taking here?
That's a good point. There are none. That's thanks a lot for pointing that out. So I forgot to say that here, in fact, we're having like fixed boundaries. So this is just like the closed segment. So the number of particles k is again conserved in this dynamics. But actually, let's now slightly change the boundary conditions. This is the second model I'd like briefly to mention. And this is the TASEP with open boundaries. So the totally asymmetric simple exclusion process, where in addition, particles can enter at the left-hand side at some rate alpha and exit at the right-hand side at some rate beta. And this is a process with a long history, for example, already studied by Liggett almost 50 years ago. And there were some beautiful results on investigating, for example, the stationary distribution of this process due to Derrida and others, Cortell and Williams, using the matrix product ansatz or tools like staircase tableaux. So this is some very interesting process in many different areas. And here for this, for the TASEP with open boundaries, one can also study like mixing times here. And it turns out that depending on the parameters alpha, beta, so alpha for the particles entering and beta for the particles exiting, we have like different regimes. So there's a regime where you see like a high density. So intuitively, this means that like that the particles that somehow, if you think of the boundaries, like at the right-hand side boundary, the particles cannot really exit the process. And in this case, you somehow create like a traffic jam within the segment. And similarly, within the low density phase, like somehow the source of particles at the left side of alpha is not strong enough in order to provide somehow the alpha dominates like the stationary distribution of the segment. So this is maybe a bit similar to the case where you're on the closed segment. And there's also like a different regime called the maximal current phase, where somehow the power of the rate of generating particles, so the alpha and the beta, they're both strong enough in order to have like that the restricting part for the density within the segment is like the segment itself. So in some sense here, we can make that rigorous, that in the low density phase, the average density of particles is less than a half. In the high density phase, it's strictly bigger than a half. And in the maximum current phase, like the overall density of particles is actually equal to a half. And there's also like some like degenerate case between the high density phase and the low density phase, namely the coexistence line. And also for these different regimes, one can study mixing times. And let me maybe just comment on one result here for this maximal current phase. That here we see like a mixing time of order n to the 3/2. And if you recall, the main result for the TASEP on the circle is that the mixing time is of order n squared times k to the minus a half. So if k is of linear order, this is like matching here like the same order. So again, the n to the 3/2 for this maximal current phase for the TASEP. And similarly, we also have like a linear regime, like in the case of the closed segment in the high density phase and the low density phase, and also have cutoff in these regimes. But let me maybe only focus like on this behavior where we see this mixing time of n to the 3/2. Okay, so this is just for like giving you the context what was done so far for this exclusion process, and let me now spend the remaining time to explain you like the ideas for the proof. So how do we actually prove that mixing terms of order n squared k to the minus a half for the TASEP on the circle? So the key idea which we use is its correspondence or its interpretation as a corner growth model. So what do I mean by this? Well, in order to introduce it, let me think of the following as the TASEP on the circle as like a periodic model on the line. So instead of like taking just a circle of length n, let me think of like the integers and place the configuration periodically. So let's say here we just have like the integers, and whenever this is side 1, having a particle, we just like unfold the circle and take like somewhere here to the right, the same configuration, just periodically. So when I do this, so let's say here we have like a particle at side 1. This is like the particle here, and also like the particle over here, like at position like n+1. And whenever I like perform a jump here, I also perform like the jump for this particle, also like in all of its periodic copies. Okay, so it's just like unfolding the circle and taking periodic copies of it. And I'm doing this in order to interpret now the TASEP as a corner growth model in a periodic environment. So taking such a periodic configuration, I map it to an interface in the plane. So here we just have Z2, and I treat now such a configuration as an interface in Z2 defined in the following way. So let's maybe just focus here on this blue part. So whenever I see like an empty side, I make one step to the right. And whenever I see a particle, see here at side 2, I make one step down. So here, this configuration, like seeing an empty side, will make one step to the right, then a particle one step down, another empty side one step to the right, a particle one step down, then two empty sides, and then a particle. Now we take this like part of the interface and just like copy it periodically. And in this way, we get like a periodic curve here in set 2. And now what I want to do is I want to fill up the cells above this curve by exponential random variables. So these will all be exponential 1 distributed random variables, and I want to have them periodically. So in the following way, let's say we focus here on this like omega 1, 1. Whenever I make in this case here like 1, 2, 3, 4 steps to the right. So in general, n minus k steps to the right, and 1, 2, 3 steps down. So k steps down. I want to end up with the same random variable. So notice it here, whenever I make, for any point here in the grid, whenever I make n minus k steps to the right and k steps down, I place the same random variable. But apart from that, all these exponential random variables will be independent. And now I want to use these exponential random variables in order to couple them with like the evolution of the TASEP on the circle, or like in this periodic setup. And I do so in the following way. So notice that here in the process, 3 things can happen. Either this particle jumps to side 1, this particle here jumps to side 3, or this particle jumps to side 5. Now I use these exponential random variables, the omega 1, 1, the omega 3, 1, and the omega 5, 1, in order to determine which of these particles will jump first. So whatever is the smallest of these like random variables, like in these corners, so whenever I have like, let's say I have a move down and a move to the right, whenever, so I take like all these random variables in these corners, and whatever is the smallest one, this will determine what will be the next jump in the TASEP. So let's say here the omega 1, 1 is the smallest. So I wait now the omega 1, 1 amount of time, and whenever the time is up, this blue particle here will make one jump to the right. And I add like the cell omega 1, 1 and all its periodic copies to the growth interface. And now I can continue to do so. So let's say the next one is this cell here, the omega 5, 1. And this will then be the amount of time I have to wait until like this blue particle here performs a jump. And again, we added them to the interface. And we can just continue to do so. So this defines like a 1-to-1 mapping between like the TASEP in like the TASEP circle here with periodic conditions, and like the evolution of this like growth interface within this periodic exponential environment. Okay. So it's a key thing that this is real like a 1-to-1 mapping, which is a very classical result, I think, going back to Rost in 1970. So what can we do with this? So using this correspondence, we can talk about last passage times and geodesics. So what I mean by this is that for any now cell in the grid, so this cell here, I can look at the set of all lattice paths which go, or which only make steps to the right and up. So let's say a path like this. And such a path making only steps to the right and only steps up, this will be like called a lattice path. And what I want to look at is the lattice path which maximizes the weight it collects until it reaches this cell omega 6, 6 in this case. So I look at the set of all the lattice paths starting somewhere here on this red curve, and look at what's the sum of all the exponential random variables which I can collect along the path. And I take the path which maximizes this weight. And such a path will be called the geodesic, and its corresponding weight will be called the last passage time to this cell. And in fact, these last passage times have also some nice interpretations, like for counting how many particles pass through a certain position in the circle until a given amount of time. But this will not be of too great importance for the talk. Instead, we are more focusing on like properties of these geodesics and the last passage times. So, for example, if I look at two cells, like here, this omega 1, 1, 4 and its periodic copy, Notice that because we have a periodic environment, the last passage times to these cells will be the same, and also the geodesics, starting somewhere here on the red interface, the cell will be the same for both of them. Okay? And in particular, we will also be interested in the coalescence of geodesics. So let's say we're in a scenario here, then notice that whenever we have like two cells and we know that there's like the last, and we know that the geodesic from this cell here to the red interface will be given, let's say, by this blue path, and from this cell, I'm guessing 6 by the other path. Then notice that whenever we know that they meet at some point, they will like jointly go all the way to the red interface. And this is due to the fact that whenever I have like somehow this cell here in common, and I would like imagine that there would be another path, then this cannot be the case, as like the geodesic is like maximizing the last passage time. So notice that whenever I know that these geodesics coalesce at a certain point, they will stick together all the way until they travel to the red interface. Okay. So in the following, my goal will be to explain that, in fact, understanding the coalescence of geodesics is the same as asking the questions about mixing times for the TASEP. So to make that claim rigorous, let me introduce some bit of notation. So I say that TRU is the set of all periodic translates of U. So all the cells which I get by going like a multiple of n minus k to the right, and then k steps down. So like all the exponential cells which are like having the same exponential random variable in them. And in the following, let's consider two lines L and L prime, which have a slope of minus k divided by n minus k, or in other words, they are parallel to like the initial growth interface. And we're interested in a property, what I like to call like the simultaneous coalescence of geodesics between the line L and the line L prime. And we say that we have simultaneous coalescence if we find some point U in the lattice, such that for any point A in the line L and B in the line L prime, there exists some periodic translate of B and some periodic translate of U, such that this periodic translate U is part of the geodesic from A to B prime. So let gamma of A to B prime be the geodesic from A to B prime, or B tilde. And this last definition is maybe a bit hard to grasp, so let me illustrate by a picture what I mean by that. So I want to say that no matter where I start, like here on the red interface, and I try to, and I look at the geodesic to some point like on this other line here, the upper red interface, which will be my line L prime, then I find like cells, like here marked in red, such that any geodesic must pass through them. So in particular, these cells act like decoupling what happens above like this red interface here from what happens like below this red interface here. Okay. So this is like the property what we want, so that we have like this coalescence of the geodesics. And I claim that this can be very useful in order to study like, or to come up with a coupling for two different totally asymmetric simple exclusion processes on the circle. And this is the following lemma. So let's say eta t and zeta t are two TASEPs on the circle started from two initial configurations eta and zeta, and assume that they are defined, both of them are defined in the same periodic environment. So we just place like some the corresponding growth interfaces for eta and zeta, but we use the same nk periodic environment for both of them. Then I claim if we have simultaneous coalescence between two lines L and L prime, then we know that eventually the two processes will become time-changed versions of each other. So they are just differing by some t, which will be random, but will be fixed, so that for all t sufficiently large, they will behave in the same way. Okay? So let me maybe give you like an idea how we show that. So the idea is to say that whenever we have like our two processes started from two interfaces, because this is the corner growth model description is like a one-to-one description, whenever we know that the processes will be like above this line L prime, let's say, then the goal is to show that whenever like they are the two processes are above this line L prime, then we know that their evolution will only depend on the initial growth interfaces by this random time shift t. So what do I mean by that? So pick up some cell or some site omega, which lies below, above this line L prime, and now follow its geodesic all the way to the red interface and all the way to the blue interface. And I claim that whenever we have simultaneous coalescence, there has to be some side V, such that the geodesic, like connecting to the red interface and the one to the blue interface, must pass through this side V. So no matter how we took this geodesic, whenever we have like the simultaneous coalescence between L and L prime, like the geodesic must pass through this side V. But now take t, the time difference, as like the difference in the last passage time from this red interface to the side V, minus the last passage time from the blue interface to this side V. Now the entire evolution of the process once it reached above this line L prime will only depend on whatever is the geodesic to the side V. So it will depend on the initial conditions only through this time difference t, but not on the initial conditions themselves. Or in other words, the two processes will eventually behave in the same way up to this time change of t. Okay. So this is like the key idea for the proof that we get that the two processes are actually becoming time shifts once we know that we have simultaneous coalescence. But of course, there are now a few things open. So first of all, I gave you this notation of simultaneous coalescence. It's not at all clear that this is actually happening. And also, whenever you're a bit familiar with the mixing times, having the two processes coupled up to a time change is also not something which is immediately giving you a bound on the mixing time. So in fact, we would need that this time change is equal to 0 to get a useful bound. And so let me give you now like the idea of how we get rid of these two issues. So for the first one, I claim that if we take the lines L and L prime to be like horizontally shifted by a distance of order n squared k to the minus a half, then one can actually show that we have simultaneous coalescence with positive probability uniformly in k and n. Okay, so this is following strategy due to Ridi Basu, Surab Sakar, and Allan Sly, what they did for IID environments. And let me give you like the idea how to do that. So consider now here the lines L and L prime. And let's say we fix some path from A to B and decompose it into like 3 different parts. So a red part here, then a blue part here into R minus and R plus, and a red part again above here. And I want to say, or want to argue, that within the red parts here and there, no matter where, so if I compare the last passage time from, let's say, A to U1, or from U3 to B, then this will be very similar to the last passage time, what I get from starting somewhere on this line L and connecting to U1, compared to starting somewhere on this line L prime and connecting to U3. So in the red areas, I assume that the last passage times are very typical. However, then I want that in this blue part here, any geodesic, which is like, or any path, like going from this line L1 to this line L prime, not touching the path restricted between U1 and U3, I want that somehow in this blue part, every path which is not intersecting this like path between U1 and U3 is of like much smaller weight than like this red path. And so in this way, if I can achieve these two things, that within the red regions, the last passage times are typical, and within the blue regions, the last passage times are such that they are very small whenever they are not intersecting the red line. In this way, I can achieve that they must coalesce with positive probability if these two events are like holding with positive probability. In the way that I can just say, okay, start somewhere on this line L, then first go to U1, then go to U3, and then go back to wherever you wanted to connect on L prime, because this will give you a better weight than, let's say, connecting somewhere from the line L to L1, and then passing through the clue bit without intersecting this path from U1 to U3. Okay, and so this is something which can be made rigorous, as I said, a strategy by Basu, Sakar, and Sly, and with a few more details as we're in the periodic setup. But roughly, the idea, as I said, is like saying, okay, we partition like the geodesic from A to B according to like these sides for the rectangles. And then what we use is that we have some good control on last passage times in an IID setup, and these bounds can also be transferred to a periodic setup. So in particular, we have very good control on the expected size and in general also on moderate deviations of last passage times. And so we then get that any path which is not intersecting like this, this blue part, the R minus, that these paths must be of much smaller weight than the geodesic restricted to be between U1 and U2. And this uses also the fact that we have good control on the geodesics, like from a geometric sense, that namely the transversal fluctuations are of order K. So this is somehow why we exactly choose like the two lines v of distance n squared k to the minus a half. So if we then look, okay, what's like the slope of some like geodesics, like optimal path connecting like 2 points on the line, this slope will be exactly in such a way that its transversal fluctuations are of order K. And this is maybe also justifying a bit like somehow why we see like this different behavior in the TASEP on the circle compared to like, for example, the symmetric setup. Okay, so if we plug in this bound to the lemma from before, we actually get now a quantified version. So we're getting a statement of the form. So if you analyze like the last passage times and like the simultaneous coalescence, so we get a bound of the form that with positive probability, we know that for all times t after some, for all times t for some large constant L to the minus 1 times n squared k to the minus a half, we know that the two processes will agree up to a time change, and this time change can in general be bounded by some quantity of order n. So as I said before, we are almost there. So if they would not have this time change t, this would in fact give us some upper bound on the mixing time. So this is a general statement. So if we would know that this time change t would be 0, and we would have this kind of control, then we would also get a bound on the mixing time of order n squared k to the minus a half in this way. And so the goal is now to get rid of this time change. And this is somehow like the difficult part. And we do that like in 2 steps. So like in the first step to get rid of this time change is to use something which we call like a random extension of the environment. So what I mean by this is, let's say we start again with our 2 initial interfaces, and we're looking at like a geodesic to some distant point here. Now, what we want to do is we want to take the environment beyond the line L and just like shift it up. So we want to insert like a random number of extra rows to the environment, such that like this part here, the geodesic gets like shifted up. And we do like this shift for both environments in a different way. So we just like insert like a random number of rows for both of them, and this random quantity is in general different for the 2 of them. And what we then need to do is we need to control, okay, by inserting like this extra number of rows to the environment, how much did we like extra create in terms of like weights for the geodesics? So we need to control how much did we like change the last passage times by like inserting these like random number of rows. But again, using like moderate deviation results for last passage times, this is something which we can handle in this case. Okay, so we're doing this in order to get the time change down to like order n to the n times k to the -7/8. So notice that if k is very small, let's say like log n, this is really not much what we gain here. So by doing this like somehow surgery to the environment, what we get is really just like this improvement by k to the -7/8. But I claim that this is in fact enough. And to get rid of the remaining time change t with positive probability. And to do that, let me maybe use essentially the remaining time to like explain you the idea for that. So we use something called the Mamin-Wagner style argument. And at that point, let me give the credit to Ron Pallet and Doyle Bream, who I think are like, so from who I know the statements. So I think it originally goes back to a paper about in statistical mechanics about the absence of a sharp phase transition, so by Mamin-Wagner. And it's in general, it's a very nice idea, which I would say is rather powerful and not too much exploited, at least so far. And in our setup, this boils down to the following question. So consider a random vector of independent exponential 1 distributed random variables xi, and again, a vector of independent exponential 1 plus delta distributed exponential random variables. So like this one's here, the xi delta. Now, the question is for a vector of length n and like perturbation delta, what is the total variation distance between these two vectors? And just by a naive bound, you would get like a bound of order m times delta just by triangle inequality, essentially. However, you can do much better, and this is like somehow the key insight. So in fact, you can get a bound of order m times delta squared. So here to the power quarter, but and some constant c, and this is not optimal, but it suffices for what we want to do. So roughly speaking, what we get here is that for a vector of length m, I can like manipulate each of the individual exponential random variables by like order 1 over square root of m without changing the law by much. And so in this case here for the exponential random variables, there is a very nice proof to see that rather immediately. So I claim that actually, instead of looking here at the total variation distance of the vectors, it suffices to look at the total variation distance between the sum of the entries of the respective vectors. So this is due to the fact that whenever I just tell you like the sum of IID exponential random variables, I just tell you the sum, then what you can do is you can just like pick, and let's say the sum is like t, then I can just pick like m points uniformly at random in the interval from 0 up to t and recover the individual exponential random variables in this way. So in fact, that's so in this case, that somehow this total variation distance is just the same as the total variation distance of the sum. Well, but if you're comparing the total variation distance of a sum of m many exponential 1 random variables to sum of m many exponential 1 plus delta random variables, well, you can change the delta like of order m to the -1/2 without changing like the law by much. So it's just comparing two gamma random variables essentially, or you can think of it via a COT. So there are many different options. Okay, but so somehow it's crucial that we get like this like slightly improved bound of order m times delta squared. And the reason is that this is actually like enough to get rid of this like remaining time change of order n times k to the -7 rate. So notice that from before we got, okay, we can couple these two TASEPs for any pair of initial conditions with positive probability up to this time change of order n times k to the -7/8. But now, if we look at the environment, how many random variables are there actually if we look somehow at the geodesic control? like a time of order n squared k to the minus a half? Well, there will be like n squared k to the minus a half times k many exponential 1 random variables. So we can manipulate all of them, or so like each of them, by like 1 plus n to the minus 1 k times k to the power minus a quarter times u for some uniform random variable between 0 and 1. And this manipulation by the Mem and Wagner bound from before does actually not really change the law of these. It does not affect like the law of these exponential random variables in a crucial way. But what do we get by multiplying each of these individual exponential random variables by this factor? Well, we can tilt the last passage time at order n times k to the minus 3 over 4. But this is now enough in order to like get rid of the time change. So what we do is we couple these uniform random variables for like the different initial configurations in such a way that we get like coalescence with positive probability. But that's exactly what we needed. So we can now apply like the coupling bound from before in order to get an upper bound on the mixing time. Okay, so just maybe to like give you like the idea. So to recap maybe the main steps. So what we got is we're first like transferred it like this question to a question about coalescence of geodesics in order to get that the two processes couple up to this time change. Then we do like the surgery to the environment to get the time change down to n times 7, n times k to the minus 7 over 8. And then with the remaining time change, this is something which we can handle using the Mem and Wagner technique. Okay, and this is how we get our upper bound in this case. And let me maybe say that on the way, more or less as a side result, we also get like matching lower bounds. So we can show a lower bound of order n squared times k to the minus a half by investigating again like this like moderate deviations for geodesics and last passage times. So understanding their fluctuations and like the deviations of last passage times using again this one-to-one mapping between the TASEP on the circle into corner growth model in the periodic setup. And in this way, we can just say, okay, we compare it to like for specific initial conditions, what is like the number of particles which we see in an interval and compare it to what it should be under the uniform distribution. And this is how we get like the lower bound, as I said, more or less just as a side result. Okay, and let me maybe come to an end of the talk by presenting you an open question. So it's something I was saying earlier, right? But let me highlight it here again at this point. So we have the nice results in the case where p is equal to a half due to IMPA. And now we also know what's happening in the case where p is equal to 1, but any other case, p not equal to a half still remains open. But it's conjectured that also in this case, the mixing time should be of order n squared k to the minus a half, and that the cutoff phenomenon does not occur. However, the problem is that we do not have like this nice correspondence and this nice interpretation of the TASEP for the ASEP as a corner growth model. So in this case, yeah, this is still very widely open. And yeah, and I think this is a good point to stop. So thank you very much, and happy to take your questions.
Thank you very much, Dominik, for a nice, really nice talk. Is there any question or comment?
So I guess the bound you get on the mixing time, okay, depends on the time you have to wait for the coalescence for the geodesics. Yeah. Can you get a better bound if you specify the initial conditions? So for instance, I guess if you start with k equal to n over 2, and you start with periodic initial condition with period 2, Okay, so just one particle, one MC site.
Mhm.
Can you get a better bound in that case, or?
Okay. It's very nice. I'm still looking. In fact, I had this question a few minutes ago on the board.
I have very good eyes.
Behind me, behind me. In fact, I think exactly for what you just mentioned, you do get still the same order.
Okay.
So, in fact, this is a very interesting question to see what can you like improve on the initial conditions. I think the idea would still be to say, what can you say about like, so whenever I say, okay, you give me an initial condition, I can interpret this as a growth interface. Now, what I can try to do is I can look at somehow like points far away and try to see, okay, can I somehow like improve? So what can I say then about like the last passage time to these points? And maybe I can then use like moderate deviation results for these like last passage times for this like far away points to say that, okay, something could not really have matched. And I think for the conditions you actually mentioned, I think there's some nice results due to Bike and Leo for like specific initial conditions. So there you can use integral probability to get like very precise control of like the distribution of the particles. And I think for the periodic conditions, I think if I remember correctly, they also get like the essential like the limit profile, I think on the scale n to the 3/2. So I think so for this like periodic initial conditions, you can be very specific what is happening, but it's only for like also certain ratios, let's say like k is equal to n/2. So and just really start alternating these things, for example.
Thank you.
Any other question? So I am wondering, how do you do to accelerate one of the processes and decelerate the other without losing that much?
Where you mean the last step or this
Yeah,
Wagner?
Because you have this different, so you have the same configuration at 2 different times, right?
Yes.
And then you say, well, I can accelerate the one that is the second one, say, and decelerate the other one, and you don't lose any.
Yeah.
This is really intriguing. Yeah.
Yes, and the thing is, like, if you would only do it like with not the Mem and Wagner bound, you would get nothing. You would only know that you can like change it at some very small scales, which you anyway have.
Yeah.
It's really using that you're having this construction
with uniforms. But how do you couple the uniforms to get that? This is what I couldn't understand.
You mean, okay, how you couple the uniforms?
Yeah.
Well, you have like, so if you check, then the last passage time will depend like linearly on the U.
Yeah.
So whatever you do to these passage times,
yes,
if I know that I only manipulate them in a part where they agree, so let's say they first coalesced, then I know they agree, and then afterwards I will change them like by the same amount. So that's a very good point. I'm cheating here a bit. I'm telling you like modify everything, but in fact what we do for the proof is we say let them simultaneously coalesce, then let them simultaneously coalesce afterwards, and only manipulate them somehow in the middle.
Okay, but you put one positive and the other negative or something like that, or
yes. So you can.
Okay. So, like, it's very well. Okay, so you have to go to the details. I don't mean.
But I think it's really not. There's not too much happening. It's really just saying, okay, you know, that I can like. So this that there has to be a coupling between like these two quantities, simply because somehow I can just choose a uniform random variable, and if I tell you, okay, I want to like have another uniform random variable, and they are just like slightly off by each other, then I can find a coupling between these two
of
uniform
course.
random variables such that they agree with high probability.
Okay.
So again, this is only a with high probability statement. So again, so this coupling can also fail, of course, with positive probability. It's with some probability, but it will be a little lower point.
Very beautiful. Thank you very much. Yes. Is there any other question? Okay, if not, let's thank the speaker.
Sundar has a question, Pablo.
Sundar, Sundar, please go ahead.
Maybe just a
hi.
small question. Nice talk. Is there let's say in the conjecture, would there be a difference if the jumps were not nearest neighbor?
Ooh, that's a good question. It's hard to say. So I would expect, but that's I'm really not sure about that. That it's that as soon as you're still having some kind of version like so for example, like this push TASEP setup. So whenever you're like this setup, you will still get the same conjecture. Whenever you are leaving it, that you're really allowing to jump over in a non-trivial way, I would expect that so I would say in general, this conjecture fails. So I think you can come up with mechanisms where you might see some different behavior of the mixing time if you're somehow leaving this integrable setup. So especially if you allow like jumping over, I think if you have something like knowing what you're interested in, and I think when you have something like that in mind, I can imagine. I'm no longer sure about this conjecture. I think I would expect it to be false and not, and really more like something for the integrable setups, so for the integrable models which are related.
I see. Okay. Well, thanks very much, Dominik.
You have to, okay. Pablo, you are off. You have to turn your, can't hear you.
Let's thank Dominik again. And see you next Wednesday. Thank you, Dominik. Very nice talk.
Thank you. Yeah, it's very nice seeing you all around. It's